It's great to see everyone here. Welcome to Saturday Morning Physics, another really exciting event that we have planned today for you. And welcome to everybody who's joining us online. I'm physics professor Tim Chupp, and together with the Saturday Morning Physics team of many, including Carol Raybuck, my co-faculty member, Professor Rachel Goldman, who couldn't be here today, Monica Wood, and her demo lab staff, and Nick, whom we'll introduce more extensively in just a moment. How many people are regular Saturday Morning Physics patrons? And you know, I can't see. I'm a bit blinded by the light, but I see a bunch of hands up. Is anybody here for the first time? Just yell out, me. Okay, great. Well, welcome to Saturday Morning Physics, and as I said, welcome to everybody online. Saturday Morning Physics is supported by you, the generous attendants and donors to our program. We also have funding from the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Walker Family. And if you'd like more information about donating to Saturday Morning Physics to keep this great program going as well as it is, please go to SaturdayMorningPhysics.org. So, today we have the multi-talented Nick Arnold and his presentation, which is entitled From Noise to Music, the Physics of a Drum. Nick received a master's degree in plasma physics from Eastern Michigan University in 2009, and he has taught undergrad physics at Henry Ford College, Washtenaw Community College, and Eastern Michigan University before he came here and joined the demo lab in 2017. In addition to his demo lab contributions that include developing new and exciting demos, he assists in teaching advanced physics lab courses, including he's helping me with a new course on instrumentation. Nick has myriad interests, including running, rock climbing, and believe it or not, drumming. And he is a founding member of the Detroit Lions drumline and is still performing with the Honolulu Boom, providing high-energy game day performances for fans of all ages, in particular, Detroit Lions fans, right? Go Lions. All right. So drum roll, please. Ladies and gentlemen, Nick Arnold. I knew that would happen.
All right, thank you, Tim. Is this working for everybody? Beautiful. All right. As Tim said, I have a bunch of interests, not the least of which being drumming. For those of you who look at that drum and don't have a lot of experience with them, brief history. The snare drum that we know today, there we go, too many buttons, has its roots in military bands. This was, I think, a picture I stole from Wikipedia during the Civil War. And as it turns out, shouting across the battlefield to yell commands is really inefficient. So you need something nice and loud, and a snare drum provides a great tool to do that. Later on, that became drum and fifes and drum and bugles, which turned into, again, this is the abridged version, turned into marching bands of all kinds. And that's where I get tied in here. So back in the early 2000s, I started drumming in my high school band. The group that the instructors I had were also part of a winter drumline. So we would compete in gymnasiums all throughout the state, and then we competed nationally. This show, we actually won our class nationally in San Diego for finals. So got a gold medal from that one. As I graduated high school, I kept drumming, played at EMU. I'm the tall one there. That's a theme here. Played with them for 3 years while I was getting my undergrad degree. At about the same time, the instructor at Eastern had some connections with the Detroit Lions, and so we went down to the city, performed for an empty stadium. There were some executives on the top ring, saw what we did, liked what we did, and then they gave us a job as the official Detroit Lions drumline, which has been a source of a lot of interesting experiences over the last 17 years. This one is one of my favorite pictures from recently. We were part of the halftime show on Thanksgiving with Andy Grammer. And I told my parents that I was part of the halftime show and they should watch it. What I didn't tell them is I was this close to the main performer. So it was a shock for them, and someone took a picture of a television and sent it to me, so that's why I have this one. And this was from early this year. I'm still performing with the group, and it is an absolute blast. And I want to actually thank the director of the drumline there for loaning me the drum I'm using today. So thanks, Todd. So that takes me to part one, sound. And so what is sound? And the definition that I keep coming to is that it's a longitudinal pressure wave in air. And that's a lot of words, so let's break this down. Let's start with, I think we can treat air as a given. We all know what air is. But let's talk about that pressure. So if you take some air molecules, put them in a box, they're flying around at about 340 meters per second. And when they bounce off the walls, that collision imparts a bit of a force to that wall. And if you look at the cumulative effect there, that pressure on the walls of the vessel, that force on the walls of the vessel is what we call pressure. And the air that you are breathing right now exerts quite a bit of pressure on you. This bar is 14.7 pounds of steel. Has a cross-sectional area of 1 square inch. And so the atmosphere pushing down on you is equivalent to one of these bars pushing every square inch of your body, which is a lot of pressure. And it turns out the reason you don't notice that is because you push back on the air just as much as it pushes on you. We are sensitive to changes in pressure. When the weather changes, you might get headaches or feel your joints creak a little bit. For sound, the amount of pressure change in the air that we can detect, the absolute limit is about a billionth of a Newton. And so that's a 10 billionth the weight of my full water bottle in my hand. Very, very, very small amounts of pressure on your eardrum is enough to let you notice that sound exists. So that is pressure. Longitudinal is another fun word, and all that means is that disturbances in air go in the same direction that the sound wave propagates. So this is a little animation. The black dots correspond to air molecules, and you can see there's places where the air molecules are bunched up. Those are places where the pressure is increased, and places where the molecules are further apart. There's places where the pressure is decreased. And a nice way to show that is with some gas. Okay? At this point, the pressure in the tube is about the same, and so you see the same amount of gas blowing out of each hole, and so the flames are all the same height. If I add a sound wave to it, places where the pressure is increased should push more gas out, meaning bigger flames. Places where the pressure is lower should be less gas and smaller flames. The only difference here being this giant speaker pushing air at this little membrane. An example of a non-longitudinal wave would be this pulse that I send down this rope. I'm going to take the pulse and I'm going to move it, what's called transverse to the propagation. So the wave is going to travel that way. I'm going to make a transverse oscillation vertically here. The science behind these two waves is very similar. The math actually is the same equations, with the exception of a direction of a disturbance. So I tend to think of the physics of longitudinal waves and transverse waves as very similar. Last question, what is a wave? This gets a little more tricky. In my world, a wave is anything that satisfies the wave equation. So here's the one-dimensional wave equation. Looks scary. I promise it's not too bad. The letter U describes the disturbance to a medium, whether it's the location of the string here or the pressure inside the gas. And that first term on the left tells you how much that little bit of disturbance on the string is going to accelerate. The partial derivative on the right side tells you how concave the string is at that point. And c is the speed of the wave. Not the same c as the speed of light in this case, just the speed. For sound, we're looking at 343 meters per second. It's going to be significantly slower on this rope. Solutions to this equation look like this. It's going to describe some position of the rope as a function of space and time. We get a pulse that travels to the right or a pulse that travels to the left. No reason to pick one or the other, so we'll add them together. So solutions to the one-dimensional wave equation are pulses that travel right and pulses that travel left. So here we go, I'll send a pulse down. Hits the end, bounces back. So it travels both right and left. The only reason that I started swinging the rope from one side is because it's hard to move that end as well. But there's no reason that waves can travel from one direction only. So here's two waves traveling in opposite directions. When they meet, they add together and then pass right on through, maintaining the original shape. This is why if someone across the room shouts and someone over here is talking to you, people on opposite sides can hear it. The sound doesn't get destroyed when it interferes with each other. So loosely, sound is a longitudinal pressure wave in air, and I think we've covered all the pieces. Now, how do we make these oscillations in air? How do we make these sounds? Let's continue with this rope for a minute. Okay. So as I just showed, when I make a pulse, it hits the fixed end at the wall and reflects back. Okay. When it reflects, it's upside down. That's just because the wall end is fixed. And if I am clever about how I make waves, I can send pulses down, and the reflection gets to me at the same time as the new pulse, and I create a very big wave out of a very small input. This phenomenon we call a resonance. We also refer to these waves as standing waves. If I send pulses more rapidly, I can get a different standing wave, but this gets pretty tiring pretty fast. So I can make that standing wave pattern, I can make this standing wave pattern, I can make a third, and it turns out it's a lot easier to do that when you mechanize the whole thing. So here's that first standing wave. If I increase the frequency of pulses, I can get more standing waves. For a sufficiently fast pulse, I can get any number of little pieces of standing wave here. Each of those standing wave patterns in music is typically called a harmonic. So the wave equation has more than the traveling pulse solution. So for standing waves on a string, the solutions to the wave equation look like this. The first, or the middle sine function here, encapsulates how the string is shaped. The second sine function tells you how it evolves in time. The second one has the frequency, and the first one has the shape. There's a parameter in there, n, because you can have any number of standing waves on this string. So n1 was that single pulse. If n is 2, that's the 2 half waves. N is 3, that's 3 little sections. And so n can be any integer. And with that, we also end up with a new frequency. The frequencies of those oscillations on a string depend on how tight the string is, the tension in the string T, how heavy the string is, that's the parameter mu there, the length of the string L. But for my purposes, I always think of it as this. The frequency of any harmonic is the number of the harmonic times the first one, the frequency of the first one. So if the first oscillation happens at 10 pulses a second, or 10 hertz, the second harmonic is at 20 hertz, the third is at 30 hertz, and so on. Nice, evenly spaced frequencies. As much fun as standing waves on a string is, this is supposed to be about sound. So here is a sound-producing wave on a string. And the way this works is as the string vibrates, the vibrations get transferred into the body of the guitar, shake the top, makes air come out of the hole. So you're hearing the body resonate, not so much the string. But the resonance of the body depends on what the string is doing. So if you want to view some sounds, you can download the program Audacity onto any computer. It's free, works great. And as far as I know, they're going to keep it free forever. We'll see if they keep to their promise. But there's a whole host of programs that you can download to do this. But what we'll do is we'll record a sound wave. Beautiful. Okay. One of the things we can do is zoom in and take a look at the wave that's actually being produced. And uh-oh, that doesn't look very sine wave. It's kind of siney, but there's other things happening there. Before I forget and walk away with that. Part 3, Fourier analysis. So in the 1800s, Joseph Fourier was a French mathematician, and he was doing some studies into heat flow in bars. So you could heat one end of the bar and watch how the heat flows from one end to the other. Among other things, when he published his results there, he had one really interesting tidbit that said any wave can be constructed by adding up a bunch of other sine waves. So I just so happen to have a multi-sine wave generator here. All right, so I'm making it a nice sine wave. You can see it on the oscilloscope screen upstairs. And if you like, we can also listen to it. That is a pure sine tone. And Fourier said if we add enough different frequency sine waves together, we can make any arbitrary wave shape. So here's another sine wave frequency. And another one. And another one. And another one. If I add all these together, that starts to look like a square wave. And if you listen to it, it doesn't sound the same as our pure sine tone. There's extra stuff happening there. Now, pick the right frequencies, pick the right amounts of which sine wave to add. You can make any shape that you want. Wouldn't it be nice if we could do that process in reverse? Take some arbitrary sound, some arbitrary wave shape, and find a way to extract out which frequencies of sine waves are adding up to make that? That's what I thought. Or, let's say, could we decompose a real sound into sine waves? And the answer is, yeah, we can do that. This is sometimes referred to as the Fourier transform, or in our case, it's going to be the discrete Fourier transform. And so we'll go back to that guitar sound. And Monica, will you plot the spectrum for me? So this is the sound spectrum in frequencies. So what this is there's a peak at about, 356 hertz? It's 356 oscillations per second. You can go to the next one. About 530, the next one. 912. If you keep going, this is telling you what frequency sound waves, or what frequency sine waves you need to add together to reconstruct that sound, or which frequencies are present in the sound we're listening to. An interesting thing here is that all these frequencies are nice and evenly spaced. Just like the harmonics on the waves in a string. And so this was 350-ish? The second one was about 700. And the third one should be about 900, about almost 1,000. So the interval between these frequency peaks corresponds exactly to the fundamental the first harmonic, the second harmonic, if I can find it. So all those possible vibrations on a string exist in the real string at the same time. It's not just one or the other, it's all of them. How much? Well, the taller the line, the more present that frequency is. The shorter the line, the less frequency, or the less present that is. So in intro physics, we typically get to the idea of harmonics and fundamentals, but we don't get into the idea that they're all present in these instruments at all times. So let's take a look at another instrument. Surprise me with which one. So this is a pre-recorded trumpet sound. I don't play trumpet. I found that on the internet. Can we take a look at the waveform? So zoom in a bit for me. Back up. Okay. If you look at the waveform of the trumpet sound, it's different than the string plucked on the guitar. But if we look at the spectrum, we still see those evenly spaced harmonics. Now, the difference in the number of harmonics, the ratios of which ones are more strongly present than others, is what makes the guitar sound like a guitar and a trumpet sound like a trumpet. Well, one more. Clarinet. All right, very clearly not a guitar or a trumpet. We'll zoom in on that. The wave shape here looks a little more sine wavy. It's got a little jaggedness to one side. Let me take a look at the spectrum again. And again, we see the composite frequencies making up that sound, nice evenly spaced frequency components. Now, this is a lovely way to analyze sounds, but I find that process of having to plot the spectrum to be a little cumbersome. And so the designers of the software gave us one other option called the spectrogram. If you could zoom out for me. The way you read the spectrogram is you imagine a single slice vertically being that Fourier plot, or that purple plot of all the peaks. And so each peak corresponds to a bright spot on the spectrogram. And so you can see on here all those frequency components existing throughout the entirety of the note. Can we look at the alto sax in the spectrogram view? All right. So the last instrument I brought ahead of time was an alto sax. Again, we see nice evenly spaced frequency components. They look like they get a little compressed at the top. It's actually a log scale. So the vertical axis is not evenly spaced, but the frequency components are. We're going to record it. So part 4, the snare drum. Now, a little bit different of an instrument, but let's take a look at the sound spectrum first. All right. Ready? And that doesn't look anything like the other instruments. So I see a big problem here. And as I was planning this talk, I realized, after trying a half a dozen different ways to get what I expected out of the spectrum, that I made a fundamental flaw. I expected to see a membrane characteristic response, and I was getting this. This is more than just a single membrane. So while I was changing the heads on this drum, I pre-recorded a single membrane sound. So if you could play that for me when it comes back up. So this was just the single top head on the drum at low tension, but I wanted to see if I could get a nice spectrum from this. Tough to see in the spectrum, but the spectrogram reveals something interesting. So there are frequency components in there that are distinct, but they don't look like everything else. Can we bring that up a little bit? Thank you. So a couple things to notice. One, on the waveform, look how short that sound is. It's very short in duration. The frequencies also don't exist for very long. It's a very quick sound. But I do have some distinct and prominent frequency components, but they are not evenly spaced. So it turns out the one-dimensional wave equation is a bad model for a two-dimensional membrane. Who would have figured? So let's take a look at the wave equation in 2 dimensions in cylindrical coordinates. And here's what that looks like. The letter U is still going to be the variable I use for the displacement of my membrane. The first component on the left is still the acceleration of that little disturbance. That big mess on the right just tells you how concave it is. But because we're in a circular coordinate system, it looks more messy. And C, again, is the speed of the wave across that membrane. There's one other condition here in order to make sure this is modeling a snare drum's drum head well, and that's we've got to make sure we're actually on a circle. So solutions to this look a little more complicated. The first part, we've got cosine and sine something something t. So this tells me how it's going to evolve in time. We'll come back to that one. But with the R there, it tells me how the vibrations in the head are going to change radially from the center out. And then this part tells me how it's going to change as you go around the drum head, an angle. Sines and cosines are reasonably well understood. This J sub m thing is a little weird. And these two parameters, m and n, can be integers. M starts at 0 and goes up, n starts at 1 and goes up. We'll make sense of what those mean here in a moment. But as a fun mouthful, J sub m is the mth order Bessel function of the first kind. And that lambda mn parameter is associated with the nth positive root of the mth order Bessel function of the first kind. And all this does is tells us that I have to have a 0 on the rim, because the head is clamped to the rim of the drum. And so we're making sure that we're scaling everything so that I have a 0 at the outside. And I don't know about you, but when I look at this, it doesn't immediately make sense what this is all telling us. Okay. So let's take a look at the Bessel function part first. This is the first order Bessel function. And it looks a little bit sine wavy. And the way that you interpret this is the left axis is the center of the drum head, or the center of your membrane. And as you go further out, that's along the axis. The red dots here indicate those zeros. And so what I could have is the entire membrane with 1 0 at the edge, all moving together, kind of like that first fundamental frequency on the string, where the entire head moves up, then everything down, then up, then down. Or I could scale this a little bit, put that second 0 on the outside, then I could have the middle going up and the outside going down. Still a little tough to visualize. When you bring the radial part in, you also get other orders. So more Bessel functions looks still kind of sine wavy, but different enough that it's not the same function. So let's take a look at some of those vibration modes for the membrane. The way I read this is the letter M I think of as numbers of lines, N being the number of rings. So for that lowest mode, that 0, 1, the entire head is moving up and then down, and then up and then down, with nothing on the outside. The 1, 1 mode has 1 ring, 1 straight line. Half of the drum is moving up while the other half is moving down, and back and forth. Okay. You can have lots of lines, you can have lots of rings, mix and match to your heart's content. The numbers on the bottom here correspond to the frequencies. If that 0, 1 mode, that just the single ring, is frequency 1, then the next mode is, instead of being 2 times that frequency, it's 1.594 times that frequency, and then 2.136, and then 2.296. So they're not evenly spaced. The frequencies here are not evenly spaced at all. I still have a hard time picturing what's happening in this picture. So I animated some of these modes for you. So these are some of the vibration modes of the snare drum head. And if you look across the top row, the upper left is that 1 or 0, 1 mode, where the entire head is moving up, then down, then up, then down. Across the top, we have 1 line in the center, where it's not moving, and then 2 lines, and then 3 lines, and then 4 lines, where the head is not actually moving along those nodal lines. As we go down each row, we add 1 more ring. So the bottom right vibration mode corresponds to the 1, 2, 3. That is the 3, 4 vibration mode. And that little animation took 45 minutes to render. Just that one bottom part. The curvier it is, the longer it takes. Now, just to be clear, the frequencies of these oscillations are not depicted here. I wanted to make them all loop at the same rate. But the wigglier the vibrations, the more frequently that has to happen. So if we take a look at that membrane spectrogram again, we see those unequal spaced frequencies corresponding with those circular vibration modes. So instead of sines, for a vibration or vibrating membrane, we have to add those Bessel functions. It's a little more complicated, but we can learn a lot with this spectrogram. Okay. And as I said, the snare drum is not just a vibrating membrane, it's two membranes. And they're different. So the top head of this drum has a head like this. It's made out of an aramid fiber weave, impregnated with some plastic. Really low stretch, so you can put really high tensions on it. Get really fast wave speeds across the surface. The bottom head is a really thin piece of mylar fabric, or mylar plastic. So it's two different membranes, and they're tuned to different tensions. There's also a shell, and that vibrates. And there's also the snares on the bottom. So hoping to get a single membrane spectrum out of the entire drum wasn't going to happen. So when I looked at the, did we measure one? Yeah, we recorded one already, right? If you could bring up the complete drum. And spectrogram view, please. So when I looked at this, I noticed some problems. The first one's a little subtle. The harder you hit the drum, the more you push it from this equilibrium position, the more tension exists in that drum head. The tension goes up, that means the speed of the wave goes up. That affects all the frequencies. So we get something we call pitch glide, where it starts off higher frequencies and lowers as the amplitude comes down. It's tough to see in there, happens really quickly. Probably zoom back out in time. I mentioned that the two different kinds of heads are tuned differently. If you imagine being on a football field with several other people playing the same snare drum with you, if you tune these two heads to the same note, they ring. And that sound exists for a long time. If you have 10 people playing the same drum, it's really hard to tell what you're playing. So we intentionally mismatched the top head and the bottom head to make a shorter sound. Those two heads don't reinforce each other, but that means that you're going to find two circular membrane spectrograms shifted in frequency. There's also those pesky snares on the bottom, which rattle against the bottom head to give it the characteristic snare drum sound, but it adds a lot of high frequency, I'm going to call it noise, to that spectrum. The shell also vibrates, and I was trying, while I had the heads off this drum, to measure that for you. The idea is you take the shell off, you give it a good thump, listen to it ring. Sounds beautiful, but I couldn't get it to pick up on a microphone well. If you've been keen-eyed, this particular manufacturer has these little posts here. These are mounted to the shell to try and reduce some of those shell vibrations. When you play a drum, you also use a stick. And the way the stick vibrates and interacts also causes issues with the sound spectrum. Again, the sound is also really short. And so it's difficult to pick up anything because it doesn't happen very long. So how do we make music from this thing? If you play a guitar, a flute, a violin, an organ, those instruments all have what we call definite pitch. The lowest frequency vibration, your brain keys in on that, and that's what we interpret as the musical note. All the higher frequency oscillations add to what we call the timbre of the sound, making each sound specific to an instrument. Don't have that here. Those instruments can play melodies. Again, vary the bottom fundamental frequency. You can play beautiful songs. I get one note. Those instruments, let's see, if you play a clarinet and you just keep blowing into the clarinet, you can have that song or that sound go as long as you want. Some musicians use a technique called circular breathing, where they can keep air moving through their instrument while they take an inhale, and they can play indefinitely. I can't do that. So it would seem that the snare drum's pretty limited. And I never thought that way. It's just different. If you play on different zones on the drum, in the middle you pick up that fundamental frequency more often, little lower pitch. If you play near the edge, you can excite those higher frequency modes pretty easily. And if you listen carefully, it's a little bit higher pitch than down here. So you have some pitch adjustment. For me, the thing that separated this from the other instruments was that you can play very quick rhythms. And so you're playing mostly with time, not with pitch. And so I put something together last night for you. This is a quick demonstration of how this all works together. However, 21 years playing this thing, the only reason I can still hear is we've got to take care of my ears. I measured this prior to us being here. Sound levels for everybody else in the room will be more on the level of a concert. However, there's no long-term damage from a few minutes of the sound. Again, 20 years doing this a lot. If I don't take care of my ears, it's a bad thing. Also, being directly on top of this head pushes a lot of air. It's a lot of pressure. My eardrums don't like it. So, if you give me a second to get my earplugs in, I'll shut this off, and we'll play a little something for you. like I said, 20 years being on top of that, earplugs are your friend. All right. Thank you very much. If anyone has any questions.
Okay, sorry. Thank you, Nick. My ears are ringing.
Yeah.
All right,
It'll go
so
away
we're going to
soon.
get set up for questions. We're bringing microphones into the aisles. About there, Connor, would be great. And while we do, I just wanted to let people know that when I was starting out in physics, my mother told me that I needed to know math. And I remember this very distinctly. She said, you need to know your Bessel functions. And thank you very much, Nick. So I know them a little better now. But I'm still wondering. I think whenever I hear Bessel function, I think of drum heads, actually.
Good.
So very good. Okay, so if you have questions for Nick, I have a list here. I guess
Good.
we'll bring out the thing for me so I don't have to put my computer on your drum.
It's not going anywhere.
If you have questions, stand behind a microphone. Meanwhile, okay. Why don't you, let's just go back to your solo for a moment here. And I don't know how many people saw, I was sitting close enough to see that you used the back of the drumstick and the front of the drumstick. Was that show or effect?
Both.
Both.
Yeah, the difference in sound from the tip to the butt is sometimes chosen musically, sometimes it just looks cool.
Just looks good.
And that's a good enough reason for me.
I was wondering what happens when you drop a stick. That's
Bring
why
a
you
second
have more.
pair.
Okay. Yeah. So another question about a snare drum. This is not a snare drum.
This is a snare drum.
This is a snare drum. So this thing's on the, how does it work?
When you hit the top head, you push air through this column into the bottom head. And as that vibrates, it bounces into these snares and they rattle. Just like a smaller snare drum you would find in a drum set or in a concert band, it's just bigger so that it can be projected farther on a field.
Cool. Here's a question.
Hey Nick, Scott Holtz, thanks for the demonstration. I've actually been interested in the physics behind the different sorts of noises, and you had the lip wind and the woodwind, and then this guy going here and the strings. You started off talking about Civil War and sending messages. They weren't doing it with a bugle. The spectrum seemed to decay very quickly. Does that mean that this is a more efficient instrument to send that energy and transmit it? Do you think that might have been part of the reason for communication?
Part of it being loud, and the rhythms are pretty distinguishable. And so if you play for about a minute or so, and you can play different, say keeping this nice and general, different patterns, one particular drum sequence will sound different than another, and that's going to travel pretty far in a battlefield.
Thank you.
It seems reasonable to me that the single one-dimensional model would match the frequencies we'd see from a guitar. And it seems reasonable to me that a single membrane drum would match the membrane model. But it doesn't seem obvious to me that a trumpet or clarinet should align so well with the one-dimensional model. Can you explain why that would be?
Yeah, so the math behind the single string does a great job modeling the pressure profile down the tube. And a trumpet or any other wind instrument is effectively just the tube, right? We put different valves on trumpets to change the length, to change what available frequencies we can get. Something like a saxophone, you open the length of the tube at a certain point, and then the fundamental is from the mouthpiece to that point. But if you look at the pressure spectrum, or if you look at the pressure as a function of distance, you get exactly the same math as the wave on a string. And that's a lot easier to show than pressure in a tube. This gets a little loud pretty quick.
Thank you.
I have two questions. One is about the interference of waves, and you can see that in the ocean and stuff like that. But is there any effect? I'm thinking about the physiological effects of sound. Okay, it's a sound wave. Inside the brain, there are waves too. There's the gamma wave when you're sleeping, which has a frequency, I think, of 40 hertz or close to it. And people are finding out sometimes that the different frequencies of sound have a different effect on the body. Do you know much about that? I mean,
So that goes beyond my experiences. I think a neuroscientist might be a better choice for that question. And so I'm going to say I don't know.
okay, then one more question, which is more physical. If you have two frequencies, which are very clearly sinusoidal, and they interfere, then you can generate some lower frequencies, right?
Yeah, so
By the interference.
You get a process called beating.
Is that important for how people sense music?
So if you have two instruments trying to play the same note and they're slightly tuned, or if they're slightly out of tune from each other, you can listen to that beat frequency, that really low frequency oscillation in the sound, and you can figure out how far apart your tuning is. And so when I was playing a saxophone back in high school, we were a quartet, and as we would play, you could listen and go, you could hear the wah, 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 wah in the sound, and so you knew the further apart those beat frequencies are, or the further apart those beats are, the closer you are to being in tune. And so you can use that to help guide your tuning to really fine-tune how you're playing.
I think sometimes when people chant or they do singing together, you can sense that wah, wah, wah between the different voices.
I have not experienced that. I tend to find most singers are more vibrato, and so they're individually changing their frequency. And I've not heard as many beat frequencies from really close matched sounds from singers. It's not to say that doesn't happen, I just don't have the experience with that.
Oh, I'm wondering, why does it seem like I feel certain instrument sounds in my heart? Not my arms, not anywhere else, it's my heart.
I'm going to venture to say that that is a physical sensation in the body. It's probably the way the air is hitting you. It's probably just a good match for a sympathetic vibration of your chest cavity. So we hit, let's see. There's a classic demonstration where we have one tuning fork that can make a second one vibrate if the frequencies are close. And so my guess is that's exactly what's happening in your body, is your chest cavity is vibrating in response to the sounds you're hearing. It's a bit like going into a bathroom and you can sing the right frequencies to get it to resonate. A bit like that.
Wondering about the comparison with different membranes for a drum, say, a skin stretched. How does that compare to this?
So, we typically use the low stretch fiber coated in plastic because it's durable, holds up well over time. Sort of original drum heads were animal skin stretched on a hoop. They sound lower pitch typically. They have interesting different characteristics, but you have to spend a lot of care to take care of that head and also to make sure it's operating at its desired tensions. There are other snare drums which use mylar top heads, again, thin plastic. It changes the characteristic sound a bit, changes the projection of the sound as you go further away. A lot of drum set snare drums will use a coated head, and it's all the same basic physics, but you'll get a slight increase in certain frequency components, and so people will pick the head they want to get the sound they're after. Is that helpful?
Hi, I'm just wondering about the video representation of if you've thought about taking a slow motion video of when you hit the drum and how that would compare to the frequencies we see either from the stick bouncing up and down or from the membrane itself moving.
Yeah, so I was trying to do a little bit of that, again, in preparation for this. It turns out the camera I had available was not nearly fast enough. So the idea is get a drum head that's slower oscillations. So I was stretching some, which fabric is that? It was Lycra over a giant speaker and trying to drive it from underneath. You could see it do things a little bit, wasn't repeatably. I didn't feel comfortable enough bringing it here to show off. High-speed cameras can spot this, and you can find some videos online. It's not something that I was able to get working quickly. And so
Would it be comparable though?
So you can see the impact in it spread out. Isolating a single vibration mode is a little tougher. And if you drive it with another sound source underneath, you can get that. It's tricky for me to manage that here.
We have an online question, and we'll come back to the room, or a couple actually. So if you create a vacuum in between the two, the top and the bottom, what kind of sound would you expect? How would that change?
Big thud. Because if you're under a vacuum, this can't oscillate very much at all. And it'd be about the sound of me hitting the table. That's what I would expect to see or to hear out of a vacuumed out snare drum.
Cool. And the holes in the side, what do those do?
Those help reduce some pressure inside. When you hit this pretty hard, the pressures inside get pretty high.
Could you break the drum head?
Can you? Yes.
Without doing that, yes.
Have I broken a drum head? Yes. It's been a while. Yes. You also break sticks. I tend to be pretty, I'll say, gentle on the equipment.
Hard to believe. Next question.
Hi. How do you tune a snare drum?
The way you tune this thing, and I still use tuning kind of loosely because it's not a real definite pitch. The way this head is mounted is just little screws, and all you do is tighten the screws. Do it all the way around, and you get increased tension, which stretches the head more, brings the lowest pitch up a bit. You really don't want to tune them down. It doesn't like that. And if you tune up too fast, you can, and I've had heads just explode across the middle, and that's not a fun day. It's similar to drum set players, except for us, the drum keys are much bigger because the tensions are higher, and trying to put the amount of tension on with a tiny little drum key isn't fun. Is that helpful?
How do you get it to be even?
So as you're originally seating the head on the drum, you can go around and you check the sort of the overtones at each of the different lugs. And you want to get them close. I've not found perfection is helpful, but if they're in the same ballpark, from that point, you can crank the whole thing up at the same tension, and it's pretty good.
So I guess humans have been drumming for a lot longer, before the Civil War even, right? On almost everything. So there are a lot of different kinds of drums.
Absolutely.
And what makes them different? So maybe just two examples. It could be a bongo and your snare.
So I like, as my first example, the timpani. It's actually a nice pitched drum, and the timpani is actually played not in the center, but it's played near one of the edges, and you're trying to excite the 1-1 mode. So that's where one half of the drum is moving down, the other half is coming up. Too far. So top row, second column. That's the primary vibration mode in a timpani. And part of the kettle underneath that is shaped in such a way so that when you push down on that one side, the air pressure bounces off the bottom and reinforces that oscillation, which allows you to get a nice clear tone. Something like a bongo is a much sturdier frame and an animal skin head stretched over the top. And so you're just getting that head vibration, not a lot of the rest of the drum vibration. But because you're selectively picking, or because you're getting certain vibrations more pronounced than others, you end up with different sounding drums. Sort of like the different harmonics and the different ratios give you different instrument sounds. Same thing happens with the drum.
How you doing, Professor?
Hi.
So my question is, there is some sound frequency that we are unable to hear, but the dog, for example, he's able to hear it. Like I did that, like a test with my dog. There was like, the Ramones that is making like sound frequency. I can't hear it, but my dog, he can hear that sound frequency. So what's the reason for that?
So our ears are tuned really well to hear between 20 hertz, 20 vibrations per second, and 20,000 vibrations per second. As we age, that upper limit comes down. The more damage we do to our ears, that frequency level comes down. But other animals have ears that are tuned to higher frequencies. And so sound exists at much higher frequencies than we can hear. We usually call them ultrasonics. And dogs can hear that. Whales communicate at sort of subsonic frequencies, lower than 20 hertz. And so if you listen to whale noises, those are kind of fun. I put some of those on this morning as we were setting up. I don't know if anyone caught that. Is that helpful?
Thank
Okay,
you, Professor.
super.
Let's say we're in a closed room
Yep.
and we had one speaker playing a noise and we had another player playing the exact frequency of sounds to make it destructively interfere. Where's all the energy going?
Let's see. That is a demo we've done frequently. You take two speakers playing exactly the same frequency, and they are propagating those waves out into the room. And if you move your head from side to side, you can get in places where the waves are destructively interfering, so the crests of one meet the troughs of another, and you get zero pressure waves at those points. The energy is still there. It's in the traveling wave. The places where you don't hear any sound, it doesn't mean there's no energy in that wave. It just means those two waves are canceling each other out. And so we won't get the entire room to be silent at the same time. It's just, I'll say there are certain places. In fact, if you are designing a concert hall, you want to try and find what that room will do, so you can either add panels to the wall or reflectors in different places to produce places where you end up with that deconstructive interference, or destructive.
Thank you.
Another online question with your indoor-outdoor
Yeah.
drumming career, which is, how does temperature affect the sound of the drum?
So when things get cold, they shrink a little bit, and so the pitches go up a little. Same thing with horns and strings. When the temperatures go up, when the temperatures go down, everything gets a little sharp. When it's really hot, things just tend to relax a little bit, pitches go down a bit. And so I guess don't tune up before you go out into the cold. Wait till you come back inside.
That was the other question. Do you retune?
For us, we typically tune up when things are getting, I'll say, distracting to us. As long as drums are in the ballpark, they sound pretty good. If they get really bad, as an example, on Monday night, or Monday Night Football this week, we had done a bottom head change on all the drums, and it takes a while for me to get up to pitch and stay there. And so I had tuned up half of the group and left the other half undone. And so we were playing warm-up, and all I could hear was just bottom heads buzzing. It was really distracting. So
You got to Monday Night Football from our
Yeah.
class.
it was a good time.
Yeah, go ahead.
You mentioned that the top head and bottom head of a snare drum are tuned to be mismatched,
Yep.
so that the sound would dampen quickly, so you could hear it more distinctly with respect to time. How would that relate? How would that be different for, say, a tom-tom on a drum set? Would you want to tune them match so that they ring more, or would you also mismatch them?
Really depends on what you're going for in your sound design. If you want a tom-tom that rings for a long time, 2 heads, exactly the same pitch, exactly the same materials on a shell, it'll ring for a while. If you want it to be short, mismatch them a little bit, or a lot of people won't have a bottom head on their toms.
2 heads are better than 1.
For some applications.
Well, if there are no more questions in the room, there's one last question, Nick, which is, does knowing the physics of the drum make it either more fun or make you a better drummer?
Makes it more fun. Does that inherently make you a better drummer? I'm going to say no, because there's still a lot of the mechanics of how you interact with the drum and how you manipulate the sticks efficiently that make a bigger issue or make a bigger impact. I think of it kind of like learning to swim by reading a book. You can know what you have to do, but you still have to be able to execute it.
Okay, great. How do you get to the Detroit Lions drum line? Practice, practice, practice. Okay, everybody. Thanks so much.
We got auditions in January.